For Christmas season 2020, Nintendo released the new Game & Watch Mario Edition. This is a reimagining of the classic Game & Watch handheld device. Anyway, a group called Stack Smashing immediately hacked the system and made it so that you could put your own code on it. I thought this was really cool, so I of course bought one because we all had a surplus of time back in 2020. So this project, most of this video was actually filmed in December of 2020 and January of 2021. And it took me 3.5 years to get around to finishing it, but I did. About 90% of it is going to be what I shot 3.5 years ago. And then I have an ending where you can see the game in its complete form. And the code is on my GitHub, links below. All right, well, enjoy this long awaited video.
Hey there, YouTube. Okay, in a previous video, I did a teardown on the new Nintendo Game & Watch. And it's a pretty cool little system. Now, since then, Stack Smashing, who were the first people to hack this and actually do the tools that actually would unlock it, they created a base library that you can load up in STM32Cube IDE. And that allows you to basically program your own games. It gives you all the base functions like the LCD layers and whatnot. So I broke the top off of a STM Nucleo, and that gives you an ST link, so I'm going to be using that. Allegedly, these cheap knockoff links will work. I'm not sure. I just know a Nucleo definitely works. So the top of a Nucleo is actually just an ST link. So I've already done a lot of research into how to make this work. I got it working pretty much up to the point where I need to do game logic, so I figured that would be a good starting point for this video. But I will talk about what I've already done along the way.
All right, so a Tapper style game. Here's what I came up with for the background. So I've got 3 rows here, tables, and then I have some kegs, right? And I drew it so there's like a high back to the chairs the customers are going to slide along. That's so when you draw the bartender running for the money or the tips, see how I have green sections here to highlight the money when the tips are lit. That's why I drew a large back here, so you don't have to explain why you can't see the bartender's legs. So we really only need to export chunks of graphics for this, like one piece of table, right? And then we just redraw it, offset. Same thing with the kegs. Of course, I had to make it new Glarus. That's actually probably going to take up more data. So the idea here is to encode this with RLE, run length encoding. And that's basically the simplest way you can compress things. Like you start with a pixel like here, and then you count how many times in a row that pixel repeats. So you log pixel color and the number of repeats, and then a lot of times it'll top off at 255, so then you just log the pixel again. So stuff like this table will compress out very easily, like the empty spot underscore, the empty part of the tip jar, and then this section here where the bartender is going to stand, we're not going to compress that out because obviously the table and the kegs are separate elements. So we have this this gross pink background. That's a pretty common color for when people do sprite transparency. Obviously, Photoshop handles transparency, but it's not always easy to export a simple file format with transparency, such as bitmap. Like if we take this, for instance, all right, so that's layer. So let's just kind of do a destructive, non-destructive edit. All right, so that's all we really need for the tab. If we wanted to be really pedantic, we could make this a separate export and then save some space here. But all right, so obviously I've already done a lot of this. So we're going to go into bitmap and then RLE background export. And this is going to be, actually it looks more like a keg. I'm going to call it a keg. All right, so now we're going to talk about color space. So this LCD, well, the LCD and the LCD controller supports all different types of color. I want to use most of it in 16-bit with transparency. So here's where you can change that. So see how we have X1, R5, G5, B5. So that fits, that's a 16-bit per pixel color. So it's storing the image in the lower 15 bits, and then the top bit is just empty padded. That's why it's X and not A. See how that one says A there? Now that would be for alpha. However, we don't have alpha transparency in bitmap unless we flatten this, but that's, I don't want to bother doing that. So what I did was I made a script to do it automatically. So we're just going to save the image, but we're going to pad it. So instead of making the color fit in 16 bits and then sacrificing a bit for transparency, Photoshop is going to make the color fit in 15 bits, leave the MSB open, which we can then pack in our conversion tool with transparency. All right, we're going to want to have our image data as these constant char strings. Well, they're not strings technically, but you know, they're basically arrays of data. And yeah, so this we can basically just load this into the STM IDE as a data string. But how do we get this? Because we have to take binary data, convert it to basically ASCII readable text. Oh man, this folder is a mess. Oh, here we go, Bitcon. So I went online and I found some code that basically does that. It converts a binary file into a C char string, right? But I modified it. I modified it to do the RLE compression, right? So you pass in the file name, blah, blah, blah. And then, okay, so what you do is you get, so this is the main, this is basically where we're reading all the colors. So we get the file index, which is in the array B, and then the I is the pointer. So we grab 2 bytes. See how we take the second byte first? So that's because it's stored in little endian, but we need to put it in big endian for the STM. Now that doesn't have to do with Indians, either, you know, the Native American nomenclature or the country. It's actually from Gulliver's Travels, where there's a political allegory in the book where they're arguing about which end of an egg to crack, the big end or the little end, the pointy end. So that's why it's endian, not Indian. So like, let's say you have this number in hex, like 1, 2, 3, 4, right? So that's the hex number you want. So how, if it's a little endian system, it will be stored in memory little end first. So 034, then 012, right? That's little endian. And then if it's big endian, it's stored in memory in that same sequence that it would appear to a human. So like, let's say this is byte 0 and byte 1. See? So that's what endianness means. So in this case, yes, the way the data is stored by Photoshop is a different endianness from the STM, which is actually a big thing to think about, like knowing the endianness of your system, because, you know, otherwise, you know, you can't just copy the data straight over. And like in this case, I'm swapping it right there. Anyway, so we say, okay, is this a new pixel? And if it is, we write down how many repetitions of the previous pixel existed. We reset the word count, and here's where the magic happens. If this word equals that crappy cyan color, we basically make this 0. So as far as the STM microcontroller is concerned, if we have a 16-bit color, well, hold on. It's technically this. It's ARGB 1555. That's the file format. So it's 1 bit of transparency in the MSB, and then 5 bits of each color, right? So if we turn off the MSB, basically if this word equals 0, that means it will be black, but also it'll be completely transparent. Else, we take the color. Remember how we said we saved the top bit? We had Photoshop avoid packing the top bit. Else, if there is color there, we OR in the top bit to make it a solid color, because the top bit is a transparency or alpha channel. So by making that bit a 1, the color appears on screen. By making it a 0, it appears transparent. So even though we're not using Photoshop to actually save the transparency data, we're using this conversion program to use the transparency key color, which is this gross cyan stuff, and we're doing the transparency that way. That way, we don't have to care about really how the source file. So if I were to flatten this out, I could make a transparent bitmap, but that's too much work. So I don't do it in Photoshop. I just have this program do it for me. Okay, so CL to compile, Bitcon C. Bloop. All right, there we did it. All right, so back over here in Windows, let's see, where's my keg? Got my keg, slap that in this folder, and then we do Bitcon, keg, bitmap, pipe it into keg, C, kaboom, done. And there's our string. Great! Now we can copy this and put it into an H file in our STM. Okay, now we're in STM32Cube IDE, which is a really pointlessly long name for an IDE. This is what you're supposed to use to develop STM apps. It's based on Eclipse, which kind of makes my stomach churn. I really do not like Eclipse. I'm sorry, Visual Studio is better. Anyway, so this code, you can find this. The Stack Smashing people have made this available. I'll have a link in the description below. But basically, they created a base project which will get you up and running with the Game & Watch. This is after you do their unlocking flash procedure, of course. So once you've turned the Game & Watch basically just into a generic STM dev board, then you can load programs onto it in this way. And if you think about it, like what you get with the Game & Watch, you could not get all those features for $50 if you bought it like a dev board from STM. That stuff is usually like $100, right? You get a screen, you get a battery, you get a charge controller, you get an I2S audio amplifier. I mean, yeah. I mean, think about it, like a Nucleo is like what, $20, $25? They have the buttons, the flash, which I'm not using, LCD, which is important, the main, and then a bunch of, hardware abstraction layer stuff, or HAL, like the killer machine. So this is setting everything up. Again, this does it all for you. Pretty easy. Audio buffer, I'm not going to probably do that until the end. I've added an H file called GFX data, and that's where I've been putting all my strings. So this is where I would paste like the keg string. And then I have it so for the RLE decoder, it has 2 bytes each of width and height, because it could be 320 wide, which is obviously wider than a byte, and then the data. So I just commented that in. So, well, we'll get that in a second, how that works. So let's look at the pertinent areas here. Blah, 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 blah. All this happens. So there's a lot of like clock synchronization stuff going on, because this is an ARM. What is it, an ARM 7, I think? I mean, for the low-cost value line, it's a pretty powerful chip, except for it needs more flash. All right, so here's where the magic happens. Here are the 3 layers of the graphics controller, which is built into the chip. And in their implementation, they're actually using, the chip is directly driving the LCD, very much like it would like a flat panel, or, like a VGA screen. It's not sending a bunch of data over via SPI on DMA. It's actually doing a H-Sync, V-Sync, port. Well, you see that right here. So it's actually driving the LCD directly using pins. So there's actually 5 pins on the chip being used for red, 5 for green, and 5 for red, 6 for green, 5 for blue. Yes, and the reason they always bias, if it's an uneven number, it's like, oh, it's 16-bit color, so 5 bits for red, 6 bits for green, 5 bits for blue. The reason they always bias it toward green is because human eyes are most sensitive to the color green because of evolution or something. All right, so back to this. There's 3 layers. There's a background layer, right? It's just a color, right? So I'm gonna make that gray, kind of like an LCD, and I made it a little off. See how blue is a little lower? All right, so then we have 2 other layers. We have layer 0 and layer 1. So layer 0 is the one closest to the background. So as far as priority is concerned, as you, the viewer, you'll see layer 1 first, layer 0 behind it, and then the background behind that. So if you see here, I've set the pixel format to this incredibly expensive ARGB 8888. So that is going to cost us a lot. So you have 320 times 240. That's how many pixels? 4 bytes per pixel. So it's going to be 1 byte, 0 to 255 of transparency, and then 3 bytes RGB. So that's, full 24-bit color. That's going to be 300K, but you know what? This chip has a ton of RAM. It has a megabyte of RAM, which is pretty nuts for a microcontroller. I guess, what they probably did was they probably used up die space on the RAM and sacrificed the flash. Because 128 flash is actually pretty low. The alpha, the overall alpha for the channel, that's the transparency of the solid pixels. I'm going to make that a little low so it looks slightly transparent, so it looks kind of imperfect. Oh yeah, okay, CTE alpha, which is the layer, and then pixel alpha. Okay, right. So we can make both the pixels and the layer semi-transparent. You'll see why we did that a little later on. Okay, so we set the size, it's the same, background layer, none. And then down here, the topmost layer, this is going to be the segment layer, like the thing that actually simulates the LCD segments. And we're going to go with ARGB 1555, as we talked about. So the top bit is the transparency, and then we have 5 bits of color below it. And what was the screen? Oh yeah, the screen is being driven at 565. So we're losing 1 bit of green. Oh well. And also I'm going to make this even more transparent because, those characters were never completely solid. So I'm going to make the barkeeper and whatever semi-transparent. So you'll see the background bleed into the bartender, which again is technically more like a 1990s Tiger Electronic LCD rather than a Game & Watch, but whatever. So then we just initialized both those layers, and we also set the frame buffer. So the frame buffer is actually defined in the LCDC file. So I actually have 3 frame buffers. So I've got one for the background, Or, well, by the background, I mean, the graphics, like the tables and whatnot. And then 2 for the segments because we're going to use double buffering to make the animation smooth. And then if we look at the H file, it actually has the structures for these. Okay, so we have 32 bits for that because remember it was 8888. Then 16 bits for the other 2 layers. So now the question becomes, how do we put our graphics into that frame buffer? Well, we just basically copy them over. So I made this function. It's called fillRLE. Again, run length encoding. There's a pointer to the graphics, so you just pass it the address of like table, keg, digits, whatever you want. Then there's the X position, Y position, shadow, yes, no, and alpha, right? And there's well, I'll get to that in a minute. So yeah, anyway, we grab the image height and width from the data structure right there. And then we say, okay, if the image would scroll off the bottom, then we'll just reduce the height of the image. Then if the shadow is set, we're going to increase the X, Y position. So basically, we can also use this function to draw a shadow of a graphic to simulate the crappy shadow. So this is going to basically work in reverse of our conversion code. We set up our RLE count, current pixel. Line number is actually where we are in the screen buffer memory. So if it's 320 pixels across, that means we have to jump Y position times 320 to get to the next memory position for the next line. And then we just do for X, Y, and draw everything. So we say, hey, have we run out of pixels? So see how this starts as 1, right? So the minus and minus before it means that count RLE is decremented before it's evaluated, so it will always start as 0, which means it's always going to grab the next pixel. So current pixel equals, and see how it's putting together a 16-bit value out of the 2 8-bit values, right, like that. So it's basically grabbing these 2, for instance. Okay, that's our color. And then this part's kind of a mess. This is the part where it converts 5 bits per pixel color into 24 bits per pixel color. And yeah, so let me just, all right, so yeah, let's say this is 1, 2, 3, 4, 5, right? So that's our 5 bits of color in our code, but if we want that to actually fit into the output, which is a long 32 bits, we actually have to go 1, 2, 3, we have to bit shift it 3 to the right, and now it fits into the top part of 1 byte. Oh, so yeah, if you're ever chopping color bits off of something and you only have 5 bits left and you have to put it into 8-bit structure, you always move them to the left edge of your structure, otherwise it'll be too dark. But I am actually thinking about using these lower bits to add random noise later on to make it look like an imperfect static LCD. Anyway, so that's what all this does. It basically converts that. But then of course, it's a 32-bit structure. The top byte of the 4 bytes is the alpha transparency. So the reason I'm converting it to 8888 is because I want to have different levels of transparency, right? So first of all, it checks to see if the pixel's actually on screen. So for setup to draw a shadow, it will draw the image as just black, right? But it will have a variable alpha transparency, which is that right there. And see how the alpha value passed into the function is being bit shift 24 to the right? That puts it into the upper byte of the 4-byte long, or int 32, or whatever you want to call it. Well, it'd be uint 32. Else, it says, oh, has this not already been drawn? Then fill the frame buffer. All right, so the reason I did all of that, I wasted a ton of memory is so I could draw shadows, right? So I made another function. So the fill RLE just draws the graphics, but I made another function which fill RLE shadow. You pass in the pointer, but then it actually makes mostly transparent copies of it to the left, right, up, and down. See how it's only got 8 transparency out of 255? Then it makes another shadow right smack in the middle at 32, and then it draws the actual object itself. The reason I did this is so it basically creates a fuzzy edge. So instead of just having a shadow with a solid edge, you get fuzzy, 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 more solid than the object. It's clunky and slow, but the thing is we only have to draw the background once when the system boots. The rest of it is done by changing the segment LCD layer. All right, let's take a look at this on the Game & Watch. It's pretty cool. So we have our kegs and see how there's a light shadow behind them down and to the right. Yeah, so you can see the little fuzzy drop shadow. I do need to change, like if you look at like the tip jar, the text that says tip jar is not very legible, so I think I need to re-export that as a darker color. Also, there's an arrow. See how the arrow points from the tip jar to the stage? So
Once you collect 9 tips, it's going to activate the dancing girls, which will distract the customers and stop them from moving. So that should incentivize you to grab the tips because it'll give you a reprieve from their reckless onslaught. Same thing with score. I probably should just make the text darker. But it's got, it's got, obviously it's backlit, which is not accurate, but it's got a nice pastel look, and I think it's pretty good. So I guess I'll move on to the segments now, like the things that actually populate the screen.
Here's all the segments I drew for the LCD. Now, I couldn't hand draw these because there's just not enough resolution. 320 by 240 is pretty limiting, so I had to basically draw pixel by pixel. Then I, could just do a lot of copy pasting. So we got our bartender here. He can wipe the bar. See the 2 segments? He can get punched by the last patron if he doesn't get the beer in time. He can also fill the beer. Click, click, click. 3 clicks to fill the beer, kind of like Mario Cement Factory. The beer can break, right? Then he can whoosh down here and go after... He can go after the empties before they reach the end or grab the tips that are left behind, right? Here are the patrons. I realize there's 12 of them, so it's kind of like the Last Supper. Not intentional. Although, this kind of, this little interaction here does kind of remind me of the Last Supper. So here's the beer segments, right? So you've got this frothy foam that's displayed when the beer is being thrown toward the customer. So it'll be filled and there's foam. Then you can turn off the foam and have the customer just sit there and drink it, like if the customer drinks it before they take it back off camera. Then this line, that's meant to show motion when the beer is empty and it's coming back toward the player. So I packed that pretty tightly. What else? Oh yeah, so the tips. So I have a little bit of green in the background. It's actually not super noticeable on the actual screen, but it's just there to highlight the tip a little bit because you can't actually draw a proper dollar bill. But if you make it green, you give the illusion of it. It's an illusion, Michael. Then up here we have the score, 4 digits. That was pretty common. Game A, game B. Whether or not music's enabled, I don't know. It'll go there. The dancing girls, as I mentioned, you collect 9 tips, and the girls activate and make the patron stop moving. So we have each girl has a static head, body, 1 leg, and then their arms, hair, and other leg move, and then they're just repeats of each other. How do I export them? Well, this part's a bit laborious. Although, obviously you don't have to export every segment. A lot of them are the same. Although there is some difference. Like, see when the guy's moving down for his tips, he changes. I kind of base that off like Mario Cement Factory where, they have a lot of interesting poses for Mario as he moves around. So I guess he lost his job as a plumber and he has to work in a cement factory. All right, so we can take the bartender himself. So we're only going to grab the pixels we need, which is that. Okay, so then this is, which bartender is this? Barkeep 10. So we should be able to just grab that and then do a new document. All right, obviously that's very small. All right, there's our barkeep. And yeah, we can just export it just like this. So what we can do with this graphic is we can export it as bytes since it's obviously monochromatic. We'll remove any pixels that aren't relevant, like this punch animation stuff. So we remove that. We remove his arm animation. And so what we'll do here is we'll make another program, a different converter that will export this as bytes since it's either just on or off. So let's see, 1, 2, 3. So that would be a byte, and it's 24 wide, so it's exactly 3 bytes. Yeah, so instead of having to store this as 16 bits per pixel, we can store it as, what would that be? 1 byte for 8 pixels. So we can save a lot of memory that way. All right, let's look at the conversion program. All right, this program I called Segacon, segment converter. It's pretty much the same thing. So yeah, we go from the beginning of the bitmap or past the bitmap header data to the size of the image. Now, actually, to simplify this, I just export these as RGB bitmap just to make it simplified. Although the one thing you have to do, bitmaps actually store the data from the bottom up, so you have to select reverse row order. I mean, I guess I could just draw them that way on screen, but I don't know. I just like drawing things from the top down. All right, so here's how this works. Obviously, since we saved it as RGB, there's 3 bytes of color data per pixel. Of course, everything's either black or white, so we can look at just the first one. So we have our loop set up to I plus equals 3, so it's going to jump around in groups of pixels or 3 bytes per pixel. So if the first one is black, that means, yes, we want to draw a character there. So we take byte out and we OR in which bit, right? So which bit is basically a bit mask that's going to move. We started in the MSB at 80 because if you think about it with our guy here, if we're starting in the upper left corner, if you think about it, that's 7, 6, 5, 4, 3, 2, 1, 0. So we're building the bits from the left to the right. So yeah, we're basically building the bits as the way you picture them, in memory. Yeah, so which bits? Then what we do is say, okay, is which bit equals 1? So does that mean we've actually shifted all the bits? So which bit would start as, well, if you go in binary here, 1, 1, 2, 3, 4, 5, 6, 7, right? It starts as that, and then we basically compare. So basically, if we see an active pixel, we fill it, and then we bit shift it 1 to the right. So once it moves all the way over here and becomes, well, then the value of that would be, well, just be 1. Once it does that, then we know we've completed the entire byte. And then we print the byte out the same way. Then we reset bit to the MSB. And then this triggers the system to get another pixel of data. And then we just continue that for the rest of the image. Oh, yeah. Anyway, so yeah, it'll store, well, you've got this guy here. What is he? So then I put all of my graphics into this graphics H file. So we got bar keep 10. We've got wipe animation 1 and 2. And I just kind of try to put these in order as they appear on screen. So the very first thing is the score, then the stage, and the tips. I just work my way down. It just makes it easier to keep track of in my mind as well. And all right, so I made another function called fill segment. It's pretty much the same. It gets the same pointers. Of course, the segments are never going to be the full size of the screen. So I just have 1 byte for the width and height each, right? I also might make a function just to draw rectangles in case we need to draw like a line or a bar, like just a stick coming out of the keg, like before the lever is pulled, just to save a little space. Yeah, so we just do the same thing. So we say, okay, have we counted 8 bits? If we have, then we get the next byte from the memory array, which is the pointer. And then this buffer thing. This has to do with the frame buffer I was talking about. So there's a frame buffer in memory, but I actually want to have 2 frame buffers, and there's a reason for that. I'll explain it in just a bit. So basically, depending on what the buffer status is, we'll either put it into the segment 1 or segment 0 frame buffer, but they both end up in the same layer on screen, right? So yeah, we just load in a byte, and then one by one, we pick apart each bit of the byte, and if it's 1, we send out black. If it's 0, we send out nothing. And of course, see how we have 8,000 here is what we're actually sending. So we're actually sending it as black pixels, but then the thing we're changing is whether or not the MSB is set. And that's one of the reasons why I packed it in the way I did. So if you think about it, one of the reasons I bit packed it the way that I did. So let's say, let's say that's some pixel data of our guy, right? So it's 4 black pixels and then 4 transparent pixels. So what we're doing here is we take that and we actually bit shift it to the left, right? So which would be the effective of 1, 2, 3, 4, 5, 6, 7, 8. Now, if you look at it, so this is the data we're trying to clock in, and so the MSB of that data is in the same position in memory, or it's in the same position in the word as the alpha bit, not the alphabet, the alpha bit. So that's why all we have to do here is we OR in byte out and that bit. So it's like, okay, here's the byte. We're going to ignore everything else. Is there a bit in the MSB? If so, that sets a transparency. If not, the pixel is transparent. And the reason we OR it in is so that, obviously these things are drawn in squares and we don't want them to erase any other pixels. Like we don't want the bartender to erase his own arm, and that's why we OR it instead of equals it. All right. So regarding the frame buffer thing I was talking about, so I have been experimenting with this. I don't actually know when the hardware abstraction layer decides when to update its own screen. Again, it's pretty automatic deep down in the system. And so the thing is, if you want to move pixels around, you either have to erase them or you have to bitmask them. And that seems like a lot of work. So I opted just to waste memory. And so here's what I did. Where's the example? Okay, well, I'll just put the guy back in and then you can see. All right, so fill segment. This draws the bartender at position 253, 53. And I get those coordinates from Photoshop. Okay, so we draw the bartender. Then we have a variable for his wipe animation. So we either showing wipe 1 or wipe 2. All right, and then then we reset the wipe animation. Then we draw the score. I've created a decimal function for that. We basically have digits as well. So it'll take up to a 4-digit number, then it divides. If it's a 0, it just draws a 0. Else it draws up to 4 digits. And if there is, so like, let's say it can handle up to 4 digits, but if you only have like the number, I don't know, 87, the first 2 places will just be blank. They won't be zeros, which is good. And then here's where the magic happens. We do a buffer swap. So we have the buffer variable. It's either 1 or 0. So the buffer swap, let's go to that. I added that to the LCDs. Basically, if it's a 1, we tell the hardware to go to frame buffer segment 1. If it's 0, we tell it to go to 0. So what we're doing is we're basically, well, actually, if you go up here, so when we start to draw the screen, this would probably be after the game logic, right? So we erase whatever buffer we're about to use. We basically wipe it out. So we either 0 or 1. Then we're free to draw on the empty buffer, which is more convenient because then we don't have to worry about bit mass or what data is already there. We swap the active buffer in memory to point to the other buffer. So we don't draw the buffer and then copy it over into the other buffer. We basically tell the system, okay, instead of drawing from this buffer, we've got this other buffer. We erased it. We drew everything. Now switch to it. So it means you have to draw everything every time, but that's not a big deal. The system should be able to handle it fast enough. Like the segment draw routines are much faster than the RLE. All right, let's take a look on the Game & Watch.
Hey, barkeep, toss me a socially distanced beer. Hey, this is actually good social distancing because he's sliding you the beer, right? It's like contact-free delivery. Yeah, I mean, if you look at it, obviously this is zoomed in, and you can see the pixels, but in real life, I mean, the screen is not that big. It's like, what, 2.5 inches? So, yeah, the graphic looks pretty detailed. But yeah, it's kind of ironic that even with this modern screen, we actually can't get the same resolution as you could in the original Game & Watch. I mean, at 640 by 480, you probably could. You probably actually could use hand-drawn R at that point, but whatever, I'll make this work. Again, like, for $50, you could not get a microcontroller evaluation kit with this much stuff in it for $50. Not even close.
Okay, so let's check this out. We have barkeep state. 1 means that he's tending the bar. 0 probably means game over. 2 is when he's pulling the lever to get the beer. Bar animation, that's the animation frame of him wiping the counter or filling the beer. We could use that for many different things. Beer full is a flag that says, okay, did you get all 3 segments of the beer? Now you can throw it. And I guess I probably should have put this in a structure, but whatever. So there could be, well, I think you could fit 36 mugs on screen, which is incredibly unlikely. So I just made it 40. So what we can do is we can have a status for the mug, like, is the mug being thrown at a customer? Is the customer throwing the mug back? Has the mug broken, right? We can store that here. So once per frame, we just go through all 40 possible mugs, and then we make decisions based off their status. And then what we can do if a mug breaks or if it's drank, we could despawn the mug and then use that slot to spawn a new mug, right? Yeah, so state, position X, Y, mug counter. So basically this is how fast it moves. So for each mug, this counts up from 0 until it reaches the speed value. The reason why I have a separate counter for each mug is if you have a universal counter, the bartender might throw the mug when the counter is not at the start or the end, which means the first frame of animation of the mug might be truncated. Yeah, I mean, again, we have tons of RAM. Who cares? Oh no, I've come a long way from that tiny project. So draw barkeep. We get the buttons. We'll probably do all the button analysis here. If the barkeep is not pulling a beer, then draw the bar handle straight up, not being pulled. So barkeep state, this is the first state. We already did this where he's just wiping the counter. But there we also check, okay, do we push the A button? If the A button is pressed, then we start filling the glass, right? And we don't need debounce on this because it's about holding the button down. So we'll probably add debounce, though, to the movement. That we had to like tap up every time you want to move or tap left and right. If you do push the A button, we change to state 2. So here's state 2. So we're going to draw the bartender in his pouring animation, draw the empty mug that gets filled, then we increment the animation. And this is a bit kludgy, but it will work. So basically, after 3 frames of animation, then we show his arm moving, so that way he moves over, and then you see him pull the arm. That'll give it a little bit more visual interest. But if he's not pulling his arm yet, then we still draw the upright tapper handle. And then here we basically count up the bar animation, 5, 10, 15 clicks. And that's where we draw the 3 rectangles filling the bar glass. And then once we get past 15, we just manually set the value to 16 so it doesn't go any higher. Because if you could eventually roll over past 255 and then you'd be back to state 0 again. And that's how you get glitches. And then if the button is released, so basically if not button, we change the state back to 1. Glass was filled enough, we spawn a mug. Now we'll have a separate function for spawning a mug, but I'm just using position 0. So we said the mug's on. Here's its XY position, and I'm just doing this based off of this one right here. Now, once we get this part working, then I'll make offsets for all 3 positions. But just for now, I want to make sure the animation works. Yeah, and then we reset bar animation to 0. One of the reasons we do that is so that his arm will be in the outstretched position of the wiping animation, which will kind of allude to the fact that he threw it, right? His arm outstretched. Yeah, then we also will call draw mugs from the main draw routine. We just go through all 40 possible mugs. If the mug is active, then we go into a switch case. I guess we could also just have a case 0 if it's inactive, but whatever. I mean, this is a 240 megahertz processor. I think we'll be fine. So we always draw the mug, right? Because remember, we're erasing the frame every time. But if the counter for that particular mug equals the speed, we reset the counter and then we move the mug. And then 19 is the pixel spacing between these mugs. So we're not technically drawing segments, but we're basically blending in sprites that follow the rules of the segmented display. And if it's less than -1, which means it goes off the left-hand side of the screen, then mug state equals 0, which despawns the mug. And obviously, if a customer doesn't catch it, this would be a mug break condition, but we're just testing it for now.
Now when I hold A, we'll see the mug fill. When I release it, woo, there it goes. Maybe I could have like a little bit of it spill on the ground if you overfill it, and then maybe have like a rat come and lick it up. I don't know. Yeah, see, Tapper lends itself really well to an LCD game. Maybe they just never made it because it was considered too adult. Because remember, some versions of this were called Root Beer Tapper or Mountain Dew. So now that I have this working, I need to add debounce. So like when we hit the D-pad, we'll go dun dun down down. But if you don't want it to be held up, because then your character just goes. Brrr. So I'll make it so you have to release the button before you can press it again. It's not technically debounce, but we can use the debounce like routine to do it. And I think, yeah, we did that in the Space Invaders. Cool. Yeah, so I just need to do the offsets for the positions. And I'll probably just bake those into an array. So basically, we'll have like, bar keep vertical position 0, 1, 2, and then I'll have probably a 2-dimensional array which defines his positions, and then we'll just offset that for the animations. But, this is just a test to make sure it looks right, and it does look good. So yeah, we'll build up the bartender, get him moving up and down. That'll be the next step.
All right, so we have a structure, mug type. We have the mug state, the course position. Originally, I had it using the X position, in pixels, but I realized the patrons move in course movement, so why shouldn't the mugs? Counter speed, that's how fast the mug is moving. Remember, I had to separate those. Which row, 0, 1, 2, that's mostly so we can, well, it does 2 things. It tells us which patron it's touched, and also I have a offset. So basically, you just draw the pixels as if they're in row 0, and then it'll do the left and down offset for the subsequent rows. That's so you only have to get the pixel alignment information from Photoshop for the top row. Then we create 20 mugs. Then we have patron type. Then we create 36 patrons, which would be every single seat filled, which is pretty ridiculous. But had the patrons with their own set of speeds, but then, I mean, they do move at different speeds in the arcade machine, but it looked kind of sloppy on the LCD. It looked more like they were lagging, like they weren't updating at the same time. Rando is where we store our random number. This stores the X position of each one of the patrons as they slide down the bar. Again, this is for the topmost row, and basically if it'll automatically, well, here I'll show you. If you go up to segment will automatically adjust the XY position if you are, depending on what row you're on. That just saved a lot of headache, and the rows are spaced evenly. Whoosh, oh that's his animation when he moves around. This code is a effing mess. I should have just created a separate C file for the game logic, but congrats to the people who are trying to improve the code for the Space Invaders game on GitHub, by the way. Thanks for that. It's on draw patrons. Well, it's not just drawing the patrons, it's also doing the logic. Yeah, so what I do up here is I have a 2-dimensional array of tabletop, bar, row, and mug, right? Yeah, well, 3 rows of, tables and then 12 positions per table. So the reason I created that was so I can basically put a value in it to say, oh, look, there's a mug there, right? This mouse, I tell you, it's got like some sort of battery leak. I don't know why I don't, actually, no, I do know why I don't get a new one, because I like the way it feels. Anyway, so we put the mug number into the position on tabletop. So then when we're drawing the patrons, yeah, then we also, if tabletop bar row patron course position does not equal FF, that means it's going to be a mug number. The reason we use FF is because a mug number can range from 0 to 19. So we can't use 0 as the null state. We have to use FF. Then we change the patron state, or the patron saint. We change his state to 2, which means he's happy, he's got his beer. And then we change the mug. We say that it's also been captured. And then we say, okay, the patron owns that mug number, right? But what I think is happening is, this code, I think if this code happens at the exact same time that the move flag occurs, we miss the beer, so I probably should separate that out. It might actually make more sense to update the table thing with the patrons and then do the check. No, wait, we still have the issue. Yeah, I'm just going to do the check separately. But it's working pretty well. So I guess I'll try to fix that, and then we'll move on to before I add any of the fail states. So basically, the whole game will run. You just won't be able to fail, which is secretly why there's invincibility codes in video games, because it's much easier to test a game when you can't die. All right, I copied this whole bar patron thing, and I made another 36 iteration loop here. I guess that means I can remove this. Right, so one of these only checks to see if there's a mug collision, and the other one only moves the patron. I'll flash this over and see if there's any improvement.
So we're pouring mugs as we were before. I sped up the pour animation just a little bit. I've got the B button spawning enemies, customers. Stack smashing the Discord. They pointed me to the RNG function, the random number generator. So now we can actually give the beers to the patrons. There are a few misses where like the glass will go sailing past them. Oh, right there it happened. I think that probably has something to do with like if the mug is moving on the same frame that the patron's moving, then there'll be a miss. So what I should probably do in the code is separate the mug patron collision from the code that actually moves the patron. Because right now it's like, oh, where is patron? Oh, patron's here. Is the mug here? And if it is, then it attaches the mug to the patron. There's one of the structures for the mug basically says who owns the mug, which patron number. Yeah, I haven't put in the dancing girls yet. Oh, I do. Oh, yeah, there's another miss. Yeah, also, if you tap to the left, he will go and make a dash for the change or the bottles, and they've got like a little dash animation there. Yeah, and if you're doing that, you can tap up to teleport, right? So you can get back quickly if you need to. All right, let's take a look at the code that makes this work, and then we'll see if we can fix the. I replicated it right there. Fix the mug patron glitch.
Don't let them tell you your life's taking you nowhere, angel. I think I'm actually going to separate the collisions out entirely. So I'll call it as its own function. So I'll check collisions, then I'll move the mugs and the patrons. And that clicking you hear, I'm eating an Altoid. I love Altoids. Wait a minute. Are we drawing the patrons? Just a second. Oh, maybe we should check the collisions after we draw everything. Okay, I created a separate function for check collisions. Basically does the same thing. Yeah, I think what was happening was if a patron moves at the same time a mug does, that's where we got a miss. So to fix it, I call check collisions after drawing the mugs and after drawing the patrons. So that should double it up, and that seems to be working. So I can move on with my life.
If I could save time in a bottle, the first thing that I'd like to do is to save every day till eternity passes away, just to spend them with you. But there never seems to be enough time to do the things you want to do once you find them. I looked around enough to know that you're the one I want to go through time with.
Copyright strike that.
STM32 in this thing is actually pretty powerful. It's a Cortex M7, I believe. It's got a dedicated graphics processor, so drives the screen really easily. It's 2 graphics layers, I believe, with 2 graphics layers with transparency. So
plus a background, which is a solid color. So I have a solid gray background. And then the first layer, I have RLE compressed graphics, like the tables and the kegs and whatnot. So it just only has to draw that once, and then the rest of the game, it's basically just drawing black pixels with alpha transparency either on or off for the bartender and the patrons. But the thing that's cool about the layers is you can actually say, hey, I want layer 2, which is the one holding the black segments. I want it to be like only like 80% opaque, and then on top of that you can make it either on or off. So I don't know if you can, probably can't see it on the camera, but like the background bleeds through the LCD characters a little bit. And then on top of that, after it makes the RLE backgrounds, it does a noise pass to give it a little bit of granularity. But yeah, the Game & Watch is for $50. It's a really awesome STM32 development kit. Of course, when this thing came out, well, actually, no, this was 2020, so the chip shortage hadn't started yet. But yeah, I think like they were still making STM32s. You just had to be Nintendo to get them.
Well, there you have it. My own port of Tapper called Beer Slinger on the Nintendo Game & Watch Mario Edition from 2020. I'm glad that I finally got this finished after almost 4 years, and I hope you enjoyed the video. We'll see you next time. Oh, also the code is on my GitHub, links below.